Hello everybody. Today we have a special guest, Jens-Matthias Bohli. He's a cybersecurity researcher working for Hochschule Mannhein in Germany. He is a person who is researching in security for IoT, and we have the honor to have him making a presentation. So, Jens, welcome, and when you uh, when you want, you can start your presentation.
Yep. Okay. Thanks for the invitation and yeah, thanks for the introduction. Yes, I'm working at Hochschule Mannheim, doing their work, teaching and research in the security area. Now I have the subtitle added to the talk, Embedded System and Medical Devices. And see here, if you look at our homepage of the school, so I'm in the department for technical computer science. So there is also a computer science department and there is an electrical engineering department, and we are somewhere in between with our department. And here you see this. Can you see my mouse? No, I'm not sure. Probably yes. Hopefully yes. So you see on many places here hardware and software.
We don't see your
Uh, we,
screen
we are seeing you, but not your presentation.
You're not seeing my
or
presentation
screen.
anymore.
No.
Then let me see what I did wrong. I should start it again. Where are we? Uh-huh. Now
Yeah,
you can.
we
Yeah.
can see you.
So,
We
okay.
can see the presentation now.
Just saying, yeah, it's the subtitle Embedded System and Medical Devices. And this is our homepage. So we are the department between electrical science and computer science. And so here, hardware and software, you will see it's in German, but you will probably see there's a lot of hardware and software. So our department is working on the interaction between hardware and software code, which is running very close to the hardware. And that's why I'm looking a bit in security mechanisms, where you can get guarantees out of secure hardware. So I will start with a very broad introduction to the Internet of Things from my point of view. Then get to some general security and privacy issues in the Internet of Things and motivate the importance. And then the embedded part, I want to have a look a bit at physical and clonable functions. And in the end, give an outlook to medical devices and what makes it in particularly difficult to do security for medical devices. So the future internet, I see like there are two things growing together. There is the Internet of Services, which mainly contains like the cloud and a lot of data. And there's the Internet of Things, which means that every small device is collecting more data and adding to this Internet of Services. Here, no, I don't see anything. Yep. So yeah, this is the two parts growing together. So we will have many devices and we will have a lot of data collected and a lot of sensitive data collected. So why is all this happening? Or yeah, that is a first step. The question: do we have already the Internet of Things, and I think we don't have it yet. So this is some examples of devices sold as Internet of Things devices, which we already have. But if you look very closely, it's always one device which has an app for it. And probably there's a cloud storage in the back end, but there's no interaction between them. So the washing machine doesn't depend on the number of eggs in the fridge and doesn't depend on the light. So there's not much interaction yet. It's starting that you can program some interactions. So I think it could be like there are some services with like if this then that, where you probably could, when your washing machine ends, turn on the light so you know, but it's not very widespread yet. So what we there have is kind of just a picture from an old project, kind of the intranet of things. What we want is the Internet of Things, where all of it really goes together. The application areas which are of interest to me is like the Industry 4.0, as it's called in Germany, this modern IT-driven industry. Then in our department, we work a lot on EHealth. We have students who study biomedical engineering and also a research department about medical devices. Then smart cities, that's again a collection of a lot of things, from all things that have to do with traffic, but also buildings, smart lighting. And I think where everyone has contact with the Internet of Things is then in the home automation space. This is kind of the three devices we have seen on the last slide, the smart light bulb, washing machine, all belongs to this area. And I think now I'm a bit generally considering Internet of Things, later a bit more, in particular the medical part. This is like the transformation. It's a picture from the Harvard Business Review. It's already 6 years ago, but it shows very nice the transformation that should happen from products like very old analog mechanical, electromechanical products to the Internet of Things, and where we are at the moment. So this is shown with some farming tractors. Maybe we can also consider cars in this space. So there's the old electromechanical tractor, which is a dump, just has an engine that keeps it running, and you do all the work manually configuring it. The first evolution, I think that was maybe 20, 25 years ago, was that every information is also available digitally, and there's a board computer which collects all the information and gives it to displays. So the driver or the farmer is informed by displays about the state of the machine. I think that was 20, 25 years ago. Where we are now is certainly here the smart connected product, where we already since a few years. So we have a product, and that comes with an app. And a big change here is, of course, that the product itself is not closed in itself anymore, but it necessarily connects to the outside. So you need to have a connection to the internet, and you connect with your smartphone, usually via the internet, to your product, and then you interact. And of course, by opening for connections, by opening connections, you get security problems. So I think here mainly it starts with the security issues. but it's not yet Internet of Things. So the next evolution step would be a product system. So here you see a lot of products from the farming space, which connect together, communicate together. I think you see it also sold these days, like those product systems. If you have two products from the same manufacturer, you have them in the same app and they can configure each other and work together. So this is here the idea. Products from the same application space, from the same manufacturer, they work together well. And finally, there's the systems of systems, and here is really everything in it, the calendar, the weather forecast, the seed optimization system. So all data which is available and which can help you in doing your task. So here in farming, you will be able to use. And then, of course, there is data which is not trusted, data from other manufacturers, data from other people, maybe private people who have weather monitoring systems. So there's a lot of data, every data which is available, which might help you, can be used. So, and yeah, this is kind of the space where then the big IT companies are in. With their vision, everything should be available and work together. Looking at security and privacy. So you might know those Google cars, and I don't know about the status in Colombia, but if you look Street view in Europe, you see there is Germany, which is kind of an empty place, and there are 2 or 3 cities only in Google Street View. One of them is Mannheim, so where I'm located. But if you open then Google Street View in Mannheim, you see again nothing. So every second, every third house usually is blurred out. And well, the reason that Germany is not in Street View is that when Google rolled it out, there was a big discussion about it, and people got upset that now there is someone looking into their living rooms and they didn't want it. And yeah, finally, Google couldn't really roll it out fully, and they only started with 2 cities, and everyone could who has an interest that this house is not shown because they live there or the house is owned by them could send to Google, I don't want my house shown on Street View, and they had to take it out. And finally, they decided it's not worth for them to roll out Street View in Germany. So now there was a big discussion, and this product was not accepted, although I think the danger is rather small if you compare it to what the Internet of Things is, because well, the Internet of Things is kind of a real-time Street View. So there have been many research papers out there which do kind of those studies, take data which are sent by maybe one product, could be a TV, or monitoring the local Wi-Fi, or look at a collection of data which goes to the cloud, and then try from this data to predict what people are doing, and this works quite well. So yeah, down here we have a smart meter, a smart metering system which is measuring like every minute the power consumption of a house, and with this data, it's pretty exact possible to predict or to guess what the people in the house are doing. Every device you have in a house has a very particular shape on the energy consumption. like the fridge is coming in periodically, then you can take it off. The dryer is taking a lot of power, but very short time. So when it's heating up, it's really consuming a lot. You see it at very high spikes. The TV is usually on in the evening hours, and so on and so on. So you know exactly when is someone at home, when is no one at home, and what is happening. So yeah, this is the privacy side, and you should always have in mind, even though there are things which are communicating, and you think your fridge hasn't anything private to tell, or your TV hasn't anything private to tell, in the end it is, because if you connect a lot of data, all data is somehow connected by people. What you have in the fridge, when you have it there, when you consume it, it's all connected to behavior of people. And if there's a lot of data, finally it tells a lot about people using the things. So that was the privacy side, but there is certainly also the security side, because the Internet of Things is changing what an internet attacker can reach. So far, like a cyber attacker can only delete data or have a crypto Trojan, so yeah, try to delete data, blackmail for money. But with the Internet of Things, someone in the cyberspace has outreach into the real world. And well, it can be distracting the traffic. Oops, this can be, okay. Here we see one which, let me see if I can move it to the front. One which is in the background. I cannot move it to the front. So, but there we have two quite severe attacks. I will come back to this attack anyway later. So we have one attack where an autonomous drone is delivering radioactive waste right to the parliament building or to the prime minister's house, which happened a few years ago in Japan. And well, what you can see here is that Australian researchers managed to activate implanted defibrillators. So give someone a high power shock at a time when the heart is working normally. Yeah, somehow this slide doesn't show. So you see, yeah, those attacks can have outreach into the real world, from rather harmless to very severe attacks which can endanger health and life of people. So that's why, yeah, we need security measures quite a lot and on all levels. So you can, such a big system with sensors that transmit to the cloud transmits back, then actuators give a response. Yeah, you cannot secure it at one place, so you need to secure it at many places. And yeah, we worked mainly at NEC. We worked quite on many of those places, starting from the information gathering, the question, can you trust your sensors? Then storing and analyzing all of it in the cloud, where we can look at how much of the processing can you maybe do on encrypted data. So how much of the data do you really need to disclose in order to get the service that you want? And finally, the question, to whom do you share the information, or how can you privately share information so that others can profit from your data without learning too much about you? So, and yeah, what is kind of the important message? So the security and privacy is one key factor, as we have seen with the Street View example in Germany. If somehow this gets viral, that there's something insecure or privacy threatening, then really it can destroy the introduction of a product. So you should always consider privacy and security, of course. No, I'm going into the wrong direction. I'm coming now to the sphere of embedded system, or what can you get from your hardware. And one thing is, of course, software cannot be trusted. Software can be very easily modified. If you have access to a system, remote access to a system, you might well be able to exchange the software which is running there, to access the keys which are in the memory used by the software, or to access keys which are stored on some kind of persistent memory, change it. Everything which is software which is stored with bytes can be changed. Well, but what cannot be changed is certainly hardware. The wiring of hardware cannot be changed remotely. And there I'm looking at the question how to store keys. And of course, key material is really what every product builds on, is that you have secure keys. This is yeah, kind of what should this say? So if you have some products, it's what is a fundamental process is always that you have to authenticate you to tell who you are. And well, usually now not you are authenticating yourself, but your device is authenticating that it is allowed into the network, that your device is allowed to open the house, to open the car, and so on. So many examples. If you make a bank transfer, basically the smart card you have, your credit card, authenticates itself to the machine, and then you get cash. Or if you use such FID car key and press, the car key is authenticating itself to the car, so the car is opening. And the question is how will you do this? And if we look at how humans authenticate themselves, there are the traditional three ways. So you use something you know, which means you enter a password or a PIN. Something you have, which means basically you relay your authentication to a thing. So the key authenticates for you, or the smart card you have. And there's something you are, which means you use biometrics. Now, if we try to look, how could the car key do it? Do we also have those three things for devices? Well, something you know, that's for the key, would translate into something you store. So that is the cryptographic key, the secret bit string, which the key has somewhere embedded, stored, and then proves to the car that it knows the key by some kind of protocol. Something you have doesn't make sense. So something you have was relaying the authentication from the human to the device. Now we are already the device, so something you have doesn't really make sense. And the question is, can there be this something you are for devices? And there we come in a minute. Why is this something to store? You store not ideal. I said already, though, if you store it, it's kind of software. It's brought to the device afterwards, like software. It's not part of the device itself. There it can be attacked by remote attacks, of course, but we should not only focus on remote attacks, we should also try to achieve security against local attacks. because sometimes the one who is owning the device, having the device in his hand, is indeed someone who could be the adversary. That's obviously for smart meters. So a smart meter is in your house, and you might have interest to reduce the numbers showing there. So to reduce the energy you consumed, or not to show the full energy you consumed, because you have financial profit from it. There is here the space of the truck driver supervision, so the smart tachometer in a truck. So the truck driver would like to drive a bit faster than allowed, but he doesn't want it to be found out. So he might be interested in hacking these devices. And maybe you have your key, your car key somewhere on the desk, you're in another room, and someone sneaking in might be interested in extracting your key here to open your car or make a copy of it. So here's temporary access. It's this thing called a lunchtime attack. You have temporary access to it and try to copy it. So there is a lot of interest even in attacking devices which you own, and the keys on it should be safe even if you do this kind of attack. There's the traditional approach, which is tamper-resistant hardware, and IBM is for many years selling those kind of devices, high security devices. Those devices are not more powerful than a usual smart card, but has a lot of sensors and shielding on it. So shielding, so there is really no radiation from the processor in it going to the outside, but also active sensors for tamper resistance. So if someone tries to open it, this device will immediately delete all the keys. If it notices temperature change, because if you freeze a device, then the electrons move slower, so you can freeze it and try to read out the key, because if it's frozen, it cannot delete the key anymore. But therefore, it has active sensors for temperature, and if the temperature decreases, it will immediately delete the key as long as it's still possible. If the temperature increases, the computational units, the CPUs, will make more mistakes, more errors, and it will also delete the keys before that happens. And also radiation. With radiation, you could burn into the memory that numbers which are actually currently stored. So before that happens, everything will be erased. But yeah, very high cost, very low capabilities. This thing cannot do much more than a smart card. It can store a key and do very basic crypto operations. And a new idea is the physical unclonable function. So the idea is to create keys from the unique features of the hardware. And every hardware, even if it's coming from the same machine or if it's chips which are on the same wafer, every chip is a bit different. So and even if it's only one layer of atoms, which maybe one chip has more and one chip has less, but they are different. So on a microscopic level, they are not identical. And the question is, how can this be used? So if we have such a thing, so if we have a physical unclonable function on it, a function which is in the same way produced on every chip, but it's always a bit different, and we can challenge it, and then it gives us a response which is always unique to this chip, then we can use this response as the key. or we can use the response to create keys with it. So it will have a certain entropy which we can use to generate keys. So such a physical unclonable function should be therefore based only on the physical system. So there should not be any software later which is brought into it. And it should be easy to evaluate. And there should be entropy in it, look like a random function. But if there's entropy in it, we can always use a hash function, then it looks like a random function. And it should be unpredictable. It should be it should have the entropy, even if the attacker is close and maybe can look at it. And typically those physical unclonable functions also have the property that if you try to physically change the device, to physically open the device, then the function changes. So you don't need this tamper detection to delete a key. The key kind of deletes itself automatically if someone is trying to break the device. If you have it, question is, what can you do with it? This is a bit technical protocol already, but we can shortly look at it. So so far as we described, this key can produce one key, and kind of you could maybe challenge it, and then it tells you the response, but then it's often no use, because then it has told you already the response. So this should motivate, well, it's not so easy. It should not immediately give you the response of the physical clonable device, because then if you used it once, someone could have learned the response. But if you have this, you can quite easily construct a protocol around it. So you could have here two interfaces. I mean, this thing has the physical unclonable device, which produces randomness. Somehow you need to know what is the randomness of this device. And this should say, if it tells you directly, it's not so good, someone else could also ask what is the randomness. So you use kind of this protocol that you have two interfaces, maybe one interface which tells with a pre-challenge to give you the secret, but it hashes the pre-challenge to obtain a challenge, and then gives you the secret for this challenge. And then later you forget the pre-challenge and you use only the challenge, meaning the hashed pre-challenge for which you get the result, or for which you know the result and can communicate encrypted with it. But the device will not, so because no one can know the pre-image with this hash function from the challenge, no one can ask the key what its secret is. So you need a bit of protocol around it to use it. How could it look internally? There are several kind of physical unclonable functions. I think I have two in here, which so you can have them on ASICs, on chips, but also on FPGA chips. So one is kind of a runway where you have two parallel, two parallel wires which go through several gates, and then you have an arbiter who decides which signal arrived first. So per design, those wires are the same length, are designed to be the same length, and the gutters are designed to be the same. But in practice, because one wire is a bit thicker, So it might, on one of them, the signal might be a bit faster, on one of them might be a bit slower. The gutters have different times until they can switch. So one direction might be faster, one direction might be slower, so that on every chip, one of them might be faster than the others. So you configure two configurations per design completely parallel, but one of them will win, and then you obtain one bit. Is the first one faster or is the second one faster? Of course, to get 100 bit or 80 bit, you have to put on your chip 80 of those racing tracks below each other, and then you get random 80 bit out of your chip. What has shown is that those ideas where you try to get many bit out of one of those physical unclonable functions, they don't work well. So one idea was that we use the challenge to get one bit, use the next challenge to get another bit, use the next challenge to get another bit, and so on. But of course, this goes all through this very limited hardware. And if you know enough of those challenge response pairs, you can compute all of them. So this idea didn't work, but it works well if you just use it once. So if you use such one configuration, one physical unclonable function to get one bit, and use it always in the same configuration, then it works rather well. And of course, this is a response, a secret response, which you should not give to the outside. The ones which try to do many bits with the same hardware, they do not work well. Some alternative approaches are, for example, there are optical ones that have been the first ones that have been developed. So there's like a photo sensor on the chip, and there's light coming in, and then there's a random coating, transparent coating over the photo chip, and this coating is always a bit different. There are random particles in it. So if you have a light, shine a light on it, the photo chip will always measure something different depending on how its random coating is. Then there's electrical coating, which is kind of the same principle. And then there are those which are really based on gates. And there's another construction here, that's the ring oscillator. So if you have odd number of NOT gates and you build a ring out of it, then it will start to oscillate with a certain frequency, and this frequency depends really on how fast those NOT gates are and how fast the wiring is. And then you can have two of them, and one of them will have a higher frequency, and then you again get a random bit, which is different for every chip. So this kind of sums up this hardware part. There are many things yet still to be explored, how you can use the process variations which you have in producing hardware as a feature, so that you have a unique fingerprint for every device you have. And if you have this, then you don't need to store keys anymore. Your device itself will be the key. So can be applied, store keys, so you can use it for protocols, and has been demonstrated on FPGA and on ASICs. And it works well if you try to use one physical clonable function for getting one bit. It works well. If you try to get multiple bit out of one physical unclonable function, then it's still open if there's a secure construction or not. Then I want to use the last minutes to look a bit into eHealth. That's kind of IoT devices. I also see it as an IoT devices. So smart medical products are used in hospitals. A medical product is also an app on your phone or software which a doctor is using, which recommends him which to find the diagnosis, that are also medical products. But I'm mostly thinking about implantable devices, which there's an example of them given, insulin pumps, right, developing fast, cochlear implants. So they made there was a lot of medical progress made in the last years. Kind of people with diabetes can have a normal life if they have such a smart insulin pump, and people can hear again. So there's a lot of progress made with those devices, and the progress mainly, or to some part, comes from connecting out with other devices, like using artificial intelligence based again on a lot of data. So a lot of progress is made by exchanging data with other devices, by storing and collecting data from the cloud, by actively controlling other devices in your body. You have several devices that talk to each other or configure each other. So there is kind of the necessity to have more interfaces, open interfaces, which of course can let attackers in, but it also gives a medical benefit. Yeah, if you want to do it, you need several interfaces. Wired interfaces might be difficult if it's implanted in your body. Near field communication, then at least it restricts communication to maybe 50 centimeter. Bluetooth to the same room, or you use Wi-Fi, and then you can maybe communicate even from 30 meters. So somehow you need interfaces if you want to use data, but of course interfaces can let the attacker in, and then it becomes what was once termed the Internet of Deadly Things, because an attack on an implanted device can very likely do serious harm or even lead to death. And in finding solutions for medical devices, I think is in particular difficult. Now, resource restriction we have always had in the IoT, but mainly it was a financial issue, or mainly it is a financial issue. How often do you have to change batteries? This increases the cost. But for an implanted device, changing the battery leads at least that there somewhere needs to be a cut, so leads to an injury, and you want to reduce the battery, or you want to increase the battery lifetime in order to reduce injuries. Then you have very new trade-offs for the security level. Well, you could easily say, well, I keep in my closed product world, so I don't use a smart connected product, but stay in my closed world. But then, of course, it brings health benefits. So it would reduce the risk of an IT attack, but you also do not get the health benefits. This trade-off between health and security is something which is very new, I think, here in this medical sphere. And then there's also the price. And for normal devices, the argument, well, of course, often is if it's cheap, then you cannot expect security. So who wants security should pay the high price. But again, for medical products, the price is also preventing people from getting the medical help. So if you are in kind of third world countries where people have less money, then they cannot buy the products when they are too expensive. So in this case, again, the trade-off might be difficult. So do you sell a product which brings, which does a good service, so which brings medical benefit, but also brings a lot of IT risk? So can you sell such a cheap product? Will it be beneficial to produce it at a cheap price with security risks, or will it be too dangerous? So that's very difficult trade-offs to make, and very difficult also ethical questions to answer. Other difficulty comes from the fail open principle. Usually you have security, the usual security approach is that you have a failed closed system that you have when you go to the ATM with your credit card and you type 3 times the wrong PIN, then you don't get back the card. So there is a failed closed system. If you fail to authenticate, then the system closes. The same you have with the car key, which we found out in one of my courses. We tried to replay the key signal to the car. And it turned out it opened when we did it very exactly, but sometimes we didn't do it very exactly. And after a few times, one of the cars really closed the radio interface and you could only open it mechanical. So until we go to the service center and get a reset on the board computer. So typically you have failed closed principle. In medical devices, you should have a failed open principle, meaning if you have a defibrillator and now it's needed, and the person who could start it maybe could be a doctor, but he is failing to authenticate, then the device shouldn't stop working, but he should be able somehow to circumvent it. But when he is able to circumvent it, certainly also an attacker might be. So also very difficult. And maybe the solution comes only when the devices are even more intelligent. Maybe we need the devices which can gather a lot of context inside the body so that the pacemaker knows if the body is healthy and in normal condition, well, then the security level can go up. But if there's a cardiac arrest threatening, then maybe you put the security level down and accept the signals which are coming from the outside, assuming there is someone who might help because the body maybe is going to die otherwise anyway. Okay, then I'm at the end. The end of the medical part. I have this pandemic slide because now we see again this trade-off is changing. People are using those makeshift ventilators because there are not enough ventilators in the hospitals, and now we see people are taking shortcuts on the vaccines and are not necessarily following the full regulation, which you usually have to do to get a vaccination in the market. So, but now we are also there accepting shortcuts and assuming that everything was done for safety reasons. We see now there is a new trade-off between safety and the medical benefit done. So then I'm really at the conclusion. There are many still open challenges in the IoT. And yeah, still a lot of research for security needed. And the two areas I'm currently interested in is the embedded side of it. So if we have hardware, how can we use the hardware to do better security? And the other thing is the medical device security. How can we find the right trade-offs, or maybe soft trade-offs which can change based on context for the medical device security? Then, yeah, thank you. And I'm open for questions.
Thank you, Jens, for your talk. Really interesting the proposal of the physical unclonable function that you show us, and the overview also of IoT applied to biomedical systems. If somebody has a question, please write in the chat or speak now. I have actually a question. I'm really curious about the concept of system of systems that you mentioned at the beginning. And I like a lot the concept because it can represent um, maybe some of the current systems of systems nowadays. But I would like to know what's the perspective that you have that we will have in the future after system of systems. What's next, like mega systems, or what will be the next step in the evolution of Internet of Things?
Oh, okay. That's a difficult question. That goes back to the beginning, right? I should be able to go back to it. What can be next after a system of systems? Kind of, yeah, I think a system of systems can basically already be everything. I think there we have a kind of, from then we have a more smooth evolution, that more and more data is coming. So the system of systems, maybe system of systems still says that those are in itself organizations, but probably there is still a lot of data out there, a lot of things out there which are not firmly belonging to a system. So kind of everyone talks to everyone, where the trust, of course, then gets more difficult. So if you have organized systems, they can trust each other. If you really are in the free space and can take everything, then of course this trust issue gets also difficult. Where maybe that's why a bit blockchain you always also hear a bit in this IoT sphere. I think that's also looking at this system of system and beyond, when you have devices that do not know each other and need to establish trust. There are some ideas that you could use a blockchain to do that.
Yeah, I think that could be interesting, because
kind of the new thing really which comes in at the system of system and beyond is that you suddenly get data from parts of the world where you don't know anything where the data came from.
Yeah, interesting. Yeah, I also think that the trustness is something that will provoke that the system of system evolves, because by sure there will be different relations between the systems depending on the trust net, and blockchain. I also think that maybe could be an interesting a key factor that could help to evolve the Internet of Things, helping to make that the Internet of Things can be secure in some contexts, and also connected with also systems, but maybe with more or less confidence depending of the trust net. Thank you, Jens. Somebody has another question? I, if somebody doesn't have any question, I will also to make a last question related with the physical unclonable function. It's a really interesting function, and I think that it has the unique. It can be unique to provoke to create the key, but in the practice, how could it be, for example, applied for devices, because the challenge, I mean, the challenge or the pre-challenge could be generated from those physical features of the IoT devices, or how the physical features of the devices are reflected in, or are impacting the challenge or the pre-challenge that is generated in the function.
Um, yeah. Yeah, the difficult part, of course, is now the device, of course, knows its key, but how do others get to know it? And there are several possibilities you could think of. So somehow it needs an initialization mode where it one time tells you what its secret is and then shuts down. So this was one approach for the physical unclonable devices who accept many challenges. That if you have such a device which accepts many challenges, then you can use a protocol around it. Then you can use a pre-challenge where it tells you the secret, and later you forget the pre-challenge and you never come back to the pre-challenge if you only have the challenge. So depending on which kind of function you need, this might work or this might not work. Sure, but the difficult part
Okay.
on the physical unclonable function, of course, is because you cannot store anything there. It comes randomly, but one time the device needs to tell the peer how it can be approached. There's another promising way, which I didn't have now on the slides, is you can use the randomness the device has, of course, to use it as a seed for a random number generator and then produce a public key secret key pair, and then you can give the public key out.
Okay.
That's probably a more promising approach, but sure requires then a bit more computing power here.
Yeah. Okay. Okay, Jens. Well, we have a situation is that the students, some of the students have class now at this time. So I think that we have to finish the talk. So I want to thank you, Jens, for your talk. Really interesting. Um, and thank you for your collaboration. And well, the talk will be stored in YouTube if somebody wants to consult it later. Thank you so much, Jens, and have a
Okay.
good night there.
Thank you. Have a good day.
Thank you.
Okay.